I'd like to start by giving an application of the Chevalier-Weil theorem. Precisely, I'd like to prove the S-unit equation theorem via Two's equation. So I recall the statement. The equation u plus b equals 1 has only finitely many solutions in S units u and b. So I've already proved this theorem using Routh theorem. Then I proved Two's theorem again using Routh theorem, and now I'd like to show that there exists a proof of this theorem which uses finiteness statement for the two equations. So suppose that OS is a ring of S integers in a number field K. Have the group of S units is finitely generated. So the quotient, the group of S units modulo perfect cubes is a finite group. So we let alpha 1, alpha n be representatives. And so the field K cube root alpha 1 cube root of alpha n contains all cube third roots of the units in OS star. So if I consider the set of places of this larger number field extending those of S, I obtain another ring of S integers. So there exists a ring of let's call S prime integers, or S prime contained in this field K prime, such that for each u in OS star, u is a cube in OS prime. So each solutions uv to this equation defines a solution xy in OS prime to the equation x3 plus y3 equals 1 by letting x, y be square cube roots of u and v. And this is a two equation. It has only finitely many solutions. So the original equation also has only finitely many solutions. The geometrical interpretation is the following. The first equation defines a line in the plane, but I prefer to view this line as a line in gm square. So u plus v equals 1 is a line in gm square, and it is isomorphic to p1 minus 3 points. I have to eliminate the point at infinity and also the points where u and v vanish, because I'm interested in S-unit equation. So I want that u does not reduce to 0 modulo any prime, and the same for v. So geometrically I'm considering an affine line minus 2 points, or a projective line minus 3 points. The second equation defines an affine curve. Let's call it C in A2. It's a genus 1 curve with 3 points at infinity, and the map x, y to x cube, y cube, which is u e, is covered. Actually is the cover from C minus the points where x0 is equal to x of 0 is equal to 0 to p1 minus 0, 1, infinity, and this is unramified cover. And Chevalier-Weil theorem says exactly that integral points on the target curve lift to integral point on the cover after enlarging the field of rationality. I could have argued in a different way. So alternative argument. I don't enlarge the number field, but I write u and v as alpha I x cube and v alpha j y cube. Here I and j as each at most n possibilities. So I consider the n square equations alpha I x cube plus alpha j y cube equals 1. And each equation defines a curve C sub ij. All these curves are isomorphic to the curve x cubed plus y cubed equals 1 over the complex, but not over the field of definitions. And now again I have a map minus 0 set of xy to t1 minus 0, 1, infinity. So since each pair uv is of one of this type for a suitable choice of ij, each integral solution to the original equation, so integral points on this curve, lifts to a rational point on the cover for at least one choice of ij. Then if I prove that each of these curves, which is a 2A curve, has only finitely many integral points, then necessarily there are only finitely many points here. So you see that in each situation we can choose one of the two equivalent formulation of Chevalier-Weil theorem. I'm sure that every one of us has used Chevalier-Weil theorem before knowing the formal statement. Now, an application of Siegel theorem. So I denote by P the greatest prime factor. So P is a function of the set 2, 3, 4, so on to the set of primes. And the theorem I want to prove, let f of x be polynomial with integral coefficients with at least two distinct complex roots. Then P of f of n tends to infinity for n tending to infinity. Of course, the hypothesis that f has at least two complex roots is necessary. If you take f of x equals non-zero constant multiplied by x minus b, you can certainly choose x in infinitely many ways, such that x minus b is a power of 2, and so the prime factors of f of n will be, for infinitely many n, just prime factor of 2a. And I'll prove the theorem. Considering the curve y equals f of x, this curve C, and consider the open set as n tends to infinity.
So, but what if Fn produces infinite many primes?
No, prime divisors of Fn.
No, so you have the greatest. Okay, the greatest prime function.
Okay. So, and I consider the set C minus the points alpha 0, where f of alpha equals 0. So this is still an affine curve. Now, suppose by contradiction that P of f of n does not tend to infinity. This means that it is uniformly bounded on an infinite set. So there exists K and an infinite set called n containing n such that for all natural number n in this set, P of f of n is less than k. Then let S be the set of places Q containing the Archimedean ones and periodic ones for all p less than k. So it is a finite set. Then f of n is an S unit. Actually, it is in the semi-group formed of S units which are also integer numbers, but I don't use this fact for all small n. And so I claim that the pair n f of n is an S integral point on this subset, this open subset of C, call it C star. Okay. And why? Because well, n and f of n are integer numbers, and moreover, f of n never reduces to 0 modulo any prime outside S, because the prime factors of f of n are all inside S. And now I claim that C star admits a smooth completion with at least 1 plus the number of zeros of f points at infinity. The curve C will have 1 point at infinity, at least 1 point at infinity. Actually, it has 1 point which in general will be singular. And moreover, in C star I eliminated as many points as the number of distinct zeros of f. So if f has at most 2 distinct roots, C star has if f has at least 2 distinct roots, then C star has at least 3 points at infinity. So by Ziegel's theorem, it has only finitely many integral points. So, apply. Now I'd like to summarize what we saw about integral points on curves. So finally, Siegel's plus Falting's theorem provide degeneracy of integral points on curves which satisfy one of the following conditions. So, at least 3 points at infinity. So, second condition, genus strictly positive and at least 1 point at infinity, or genus at least 2 and even no points at infinity. So I recall that when there are no points at infinity, so in the compact case, by integral points, one means rational points. So in the last case, we have degeneracy, which means in this case finiteness of rational points, and this is Falting theorem. So in other words, so for all curves, but P1, A1, which is P1 minus 1 point, or GM, P1 minus 2 points, or a complete curve of genus 1, I write it E for elliptic curves. And we already remarked that in each of these cases, there really are infinitely many integral points, provided we enlarge the ring of S integers. Now shall discuss this difference between the two classes of curves, those for which it is proved the finiteness in every case, and those for which it is proved that there are infinitely many points, at least for certain ring of S integers. So those of the second class, so these curves are characterized by the following properties. First, they are homogeneous spaces for an algebraic group. P1 is homogeneous space for the group PGL2. A1 is itself an algebraic group. It is the underlying variety to the additive group. And GM is an algebraic group, and E, an elliptic curve, is an algebraic group. And this is really a characterization, because if I eliminate 3 or more points from P1, I obtain a variety for which the automorphism group is finite. So in this class, group is finite. Another property is that the topological fundamental groups is abelian. So P1 and A1 are simply connected, so they have trivial fundamental group. GM has infinite cyclic fundamental group, and elliptic curves have fundamental group isomorphic to the product of two copies of Z. And here, fundamental group not abelian. There is another interesting property which differentiates the two classes. If we look at the Jacobian variety, or the so-called generalized Jacobian variety. So we have the curves of genus at least 2 can be embedded into an abelian variety in such a way that their image is not an abelian subvariety. So the Jacobian of the curve of genus G is an abelian variety of dimension G. So when G is at least 2, the curve can be embedded into an abelian variety of higher dimension, and the image is not an abelian subvariety. And for P1 minus 3 points, as we remarked, can be embedded into GM squared. And the image is a line in GM square, which is not a subgroup. And GM square is a torus, which is an example of a semi-abelian variety. In general, we define semi-abelian variety as an extension of an abelian variety by a torus. An algebraic group containing a commutative algebraic group containing a linear torus such that the quotient is an abelian variety. Such a group G is called a semi-abelian variety. So when A is trivial, is 1 point, G is a torus. if we eliminate more points, we have embedding into higher dimensional toroid. How can we obtain this embedding? Simply, if we eliminate P1, Pn, we can always find functions having, for instance, all their poles in Pn and zeros in P1, P2, Pn minus 1. And we have as many independent functions as the number of points we remove minus 1. So if we remove 3 points, we have a map to Gm square. So this embeds into Gm to the n minus 1. And again, the image is not a subgroup, not even a translator subgroup. Is it's a subvariety which generates the torus in the sense of algebraic group. The minimal algebraic subgroup contained in the image is the torus itself. Actually, all these curves have the property of admitting and embedding into a semi-abelian variety with whose image is a closed subvariety which is not in a translator subgroup, with just one exception. With just one exception, if we consider E an elliptic curve and we remove 1 point, then this open curve does not embed into a semi-abelian variety with that property. Of course, it embeds into itself, but it will be, in that case, an open subvariety, not a closed subvariety. And but nevertheless, it admits an étale cover, an unramified cover, for instance, obtained by taking the same curve and removing 2 points. We can take P as the origin of the group law and Q any point of, well, any other point, but for instance, if we can take a point of finite order with respect to P, then you will get a map to Gm. In any case, you always have here embedding to G, where G is an extension of the elliptic curve by torus. It will be a trivial extension if Q is torsion with respect to P. And by Chevalier-Weil theorem, we know that the degeneracy of integral points on the bottom curve amounts to the same problem for the cover. So up to taking a finite cover, we can say that all curves in this class have this property, and the curves on the other family do not have this property. So it is a characterization. Now, when discussing higher dimensional case, we can try to see which of these characterization of curves having potentially infinitely many integral points, or curves having the degenerate set of integral points, can extend to the higher dimensional case. For instance, one can see whether it's true that in higher dimensional case, in each time that you have infinite integral points, it is due to the action of an algebraic group. This turns out to be not true. But in one direction it is. So if a space is a homogeneous space for an algebraic group, then starting from one point you can produce a Zariski dense set using the group structure. So I start with the discussion of higher dimension. I should introduce. Well, perhaps another remark on the one-dimensional case. Every curve is of the form a complete curve minus a finite set with, let's say, R points, where R is a non-negative integer. So each curve has two invariants. The first is G, is the genus, and the second is R, points at infinity. So the number of points at infinity. And these are the only topological invariants of an algebraic curve. So two curves with the same genus and the same number of points at infinity are homomorphic. Then one can define the Euler characteristic, okay, which is 2G minus 2 plus R. And it turns out that curves in this class are characterized by the property that chi is non-positive. In this case, it's minus 2, it's minus 1, it's 0, and it's 0. And in all other cases, it's strictly positive. So again, one can try to figure out what should be chi in higher dimension, which topological invariants should be taken into account. Now some preliminaries. In higher dimension. So consider x tilde is a smooth projective variety, and the divisor x tilde we let, as in the one-dimensional case, L of D be the set of sections, so of rational functions, such that divisor of f plus d is non-negative. This is a finite dimensional vector space. And we say D is big, and some people say almost ample if the dimension of L of ND tends to infinity as n to the dimension of x tilde. So if x tilde is a curve, this is equivalent to be ample, which is also equivalent for D being having positive degree. Also, we say that a canonical divisor K sub x tilde is a divisor of a differential form of maximal degree. So if x tilde is dimension n, I take a rational n form and its divisor, so zeros minus poles, will be a canonical divisor. It is unique up to linear equivalence. Then if D is a hypersurface, we say it has normal crossing singularities. If at any singular point has a local equation analytically equivalent to the equation x1 k equals 0. K is less than the dimension of tilde. So I'll be interested in the case of surfaces. So D is a curve on the surface. The normal crossing singularities means that either it is smooth or it has singularities of this kind. So, okay. So locally it is x, y equals 0. Now I can introduce Voigt-Lang conjecture. Pardon? Well, if I have in dimension 3, I can consider the intersection of three surfaces. For instance, the intersection of three plane in P3 is okay. So Voigt-Lang conjecture says the following. Suppose that D is a hypersurface with normal crossing singularities such that the sum of the canonical divisor plus D is big. Let x be x tilde minus D, then x of OS is not Zariski dense. Actually, there is even a more precise version of this conjecture, saying that this set should be the union of a finite set depending on the ring of S integers OS, plus points which are Zariski names in subvarieties of, in closed subvarieties of X tilde, which do not depend on the ring of S integers. So for instance, for a surface, it should have finitely many curves independent on the ring of S, which might contain infinitely many integral points, plus a finite set which does depend on the number field and the ring of S integers. This conjecture has, of course, its analog in complex analysis. Complex analytic analog is states that under the same hypothesis, no map from C to X to the analytic space X of C has Zariski dense image. And again, it should be proved that there are finitely many closed subvariety of X, such that each non-constant map, holomorphic map from C to X, has its image contained in one of these subvarieties. Both conjectures are open in dimension at least 2. I would like just to show again that in dimension 1 this conjecture is exactly what I stated, so Siegel's plus Falking theorem. Still the curve. Then the degree of the canonical divisor is equal to 2g minus 2. So if T is Q1 QR, then K plus D is ample if and only if it is big. And this if and only if the degree, which is R plus 2g minus 2, so chi is strictly positive. This is the degree. So it is exactly in the case in which Siegel's or Falting's theorem give the conclusion. Now let us analyze the situation for surfaces, and by starting in the case in which X tilde is projective plane. So we shall consider surfaces X which admit a compactification which is the projective plane. For surfaces, unlike what happens for curves, the compactification, the smooth compactification is not unique. So for instance, the affine plane can be viewed as an open set of the projective plane, but also of the product of two projective lines, which is a different surface. And actually, it can be compactified in infinitely many ways. But we shall consider surfaces X for which one of the compactification is the projective plane. This means that we consider removing curves from the projective plane. So X will be projective plane minus normal crossing singularities curve. So interesting, which curve should I remove from P2 in order to expect the degeneracy of integral points on the complement? So a canonical divisor in P2 is in the class of minus 3 times a line. So it's degree minus 3. Or in P2, all curves with the same degree are linearly equivalent. So the class of a divisor is determined by its degree as a projective curve. Here, it is the class of curves of degree minus 3. So I expect that I should remove a curve of degree at least 4. So if degree of D is at least 4, then P2 minus D should have degenerate integral points. So this is the conjecture. And now what is known, essentially, the only case which is known is the case when the curve D has at least 4 components. So in particular, its degree is at least 4. I already explained that if we remove 4 lines in general positions, so if D is then the integral points on the complement, so X is P2 minus D, and integral points in X correspond to solutions of the S-unit equation in 3 variable U plus V plus W equal 1. And the S-unit equation theorem states that solutions are degenerate. So more precisely, they are contained in the dotted lines, 3 dotted lines here. So Voigt's conjecture is proved in the stronger form. There are 3 curves such that all but finitely many solutions are contained in these 3 curves. And the exceptional set, of course, will depend on O and S. According to Voigt's philosophy, it should be equivalent to remove 4 lines or any reducible quartic, or a cubic plus a line, or a conic and 2 lines. But the problems are much more difficult if we have fewer components. I already explained that the problem of a conic and 2 lines, so integral points on complement of a conic and 2 lines, reduces in particular to considering equation of this form. Perfect square is the sum of 3 units, one of which can be taken to be 1. And this is a much more difficult problem. Here you have, if you take 1 from the other side, change the sign, u plus v plus 1 equals a unit. Here, u plus v plus 1 equals a square. All units are basically squares after enlarging the field, but being a square is much less requiring than being a unit. So this problem is much more difficult. And for an irreducible quartic, how does it become? Suppose that D is given by equation x, y, z equals theorem, where F homogeneous and supposed to be irreducible, and actually of any degree, then integral points in the complement, x is always complement of D in P2, correspond to solutions of the equation f of x u z is in its units in integers x, y, z. So we can always multiply x, y, z by constant in such a way they become integers. And we want that the point f, x, y, z does not reduce modulo any place to D, to the zero set of f. So the value of f at x, y, z should have no prime divisor, so it must be a unit. And this is a difficult problem even when f has larger degree. According to Voigt's conjecture, under the hypothesis that the curve is smooth or at least with normal constant singularities, if the degree of f is at least 4, this equation should have only degenerate solutions. But it's an open problem. The main point, the main difference between surfaces arising by removing a higher degree curve from the plane and surfaces obtained by removing several curves, for instance, a smooth quartic or 4 lines, can be seen by thinking at the so-called generalized Albanese varieties, so which means semi-abelian varieties in which you can try to embed your variety, or at least you can try to find maps from your variety to a certain abelian variety. So consider X to be the complement of a curve in P2 and search for semi-abelian varieties G and non-trivial maps from X to G. So first of all, since X is a rational variety, the compact factor of G should be trivial. So if G is an extension of those abelian varieties, then compose the map from X to G with the map from G to A, we obtain a map from X to an abelian variety which must be constant. For instance, because X is connected by lines, and every map from a line to an abelian variety is constant. So basically G must be a torus. So we can consider the case where G is a torus. So the problem is finding maps from X to a torus. And this means finding functions on X with no zeros. A map from X to a power of Gm is given by R maps from X to Gm, and a map to Gm means a functions without zeros. So we have to study which are the functions without zeros on X, and how many can you produce which are multiplicative independent modulo constant, and this will give the dimension R. Or it's clear that if you remove from P2 an irreducible curve, if D is irreducible, then every map from X to a torus is constant, because each component is a map to Gm. If you view this map as a rational function on P2, it must have all its zeros and poles in D, because outside D it must be regular and without zeros. But if D is irreducible, it then cannot contain in the same time zeros and poles. On the contrary, if D has two components, you can find a function having zeros in one component and zero on the other. So you obtain a map to Gm to the 1. If it has three components, you can have a map to Gm to the 2, and so on. And in this case, the complement of 4 lines in general position embeds this X, embeds into Gm3. And the image is the subset of Gm3 given by this linear equation. U, V, and W are non-zero, so function Gm3. So if you remove 4 or more components, you have a non-trivial map to Gm3, and then you can apply the S-unit equation theorem, which gives the degeneracy of integral points on a surface in Gm3, which is not a subgroup of Gm3 or a translate of a subgroup. If you have fewer components, you cannot do this. And that's why with fewer components, at least we cannot use result in this context is theorem of Faltings and Voiter. So first, theorem of Faltings, which says that suppose A is an abelian variety, X tilde is a closed subvariety, not a translate of an abelian subvariety, of A, then the integral points which are rational points, so X tilde of K, is not Zariski dense. And more precisely, one can say that if the set of rational points is infinite, then it is formed by finite set plus infinite families, which are Zariski dense in translate over billions of varieties. So in particular, if X tilde contains no translate over billions of varieties of positive dimension, then this set will be finite. Voita generalized this theorem to semi-abelian varieties and integral points instead of rational points. So same for X closed subvariety of semi-abelian and X OS, so integral points instead of X. Okay. So for instance, for close the subvarieties of Tori, in which case it was known before Voita, it is a consequence of the S-unit equation theorem. So in the extreme case where the subvariety is a torus, the semi-abelian variety is a torus, it is exactly the S-unit equation theorem. In the other extreme case where the semi-abelian variety is compact is Faltin theorem, and Voita proved a link between these two cases. So as I just said, these two theorems are useless in the case we are interested in the complement of a irreducible curve in P2. And actually, in higher dimension, it is rather rare that a variety can be embedded into an abelian variety, into a semi-abelian variety. Consider the compact case, for instance. Well, every curve of genus at least 2 can be embedded into an abelian variety. But, if you consider higher dimensional varieties, for instance, smooth hypersurfaces in a projective space of dimension at least 2, they never be isomorphic to subvarieties of abelian varieties. All smooth hypersurfaces in Pn of dimension at least 2 are simply connected, so they contain no regular one forms, and so they cannot. They admit no non-trivial met to abelian varieties. So this theorem is well, it's very general. You see, because it applies to every subvarieties of semi-abelian varieties without exception, but it does not apply in very natural cases. Let's see which are these natural cases. So spend few words in the case of compact surfaces. So for simplicity, let us consider surfaces in smooth surfaces in P3. Smooth. So the Voigt's conjecture predicts degeneracy of rational points as soon as the degree of x tilde is at least 5. Actually, forgot to say that Voigt's conjecture in the case of compact surfaces is actually due to Bombieri. It was previously Bombieri's conjecture. Surfaces of general type, so surfaces for which the canonical divisor is big, are expected to have degenerate set of rational points by Bombieri, actually. And in the case of smooth hypersurfaces of P3, this is the condition. So let us analyze this inequality. So for degree 1, you have a plane, and integral points are Zariski-Dines. Degree 2, you have a quadric. A quadric is a homogeneous space for a group of SO4, so for an algebraic group. So again, rational points are Zariski-Dines. Consider cubics. Cubics are smooth cubics are rational surfaces. So they admit a parametrization by P2. So if x tilde is a surface of degree 3, there exists a dominant rational map P2 to x tilde. So P2 has Zariski-Dines set of integral points, so x tilde will also have Zariski-Dines set of integrals, so which means rational points. Now the case of degree 4 is much more delicate. If the degree of x tilde is 4, then x tilde is what is called a K3 surface. And so it has a vanishing canonical divisor. So which means trivial canonical bundle. And the arithmetic on such surfaces is not well understood. But at least there are cases of quartic surfaces in P3 for which it is easy to prove that rational points are Zariski-Dines. Suppose, for instance, that x tilde contains a line. Then consider the pencil of planes containing that line. Each such plane intersects the surface in a degree 4 plane curve, which is made of this line plus another curve which must be a cubic. So you have a family of cubic curves on x tilde, and in the generic intersection will be a smooth cubic, so it will have a structure of elliptic curve, and if you find the sections of infinite order, you can have that the generic section will have infinitely many points. So by moving the plane, you obtain it's a risky dense set of points on X tilde. So at least in some cases, one can prove the density of rational points, and it is conjectured by some people that all K3 surfaces have the risky dense integral points over the risky dense rational points over suitable number of fields. On the other hand, when the degree is at least 5, it can be proved that there are no trivial ways of producing infinitely many rational points, and it is conjectured that rational points are degenerate. But there is not even one case where this conjecture is proved. We don't know any smooth surface in P3 for which Voigt's conjecture can be proved. Okay, so I think next time I will show some new results which I obtained in collaboration with Zanir, which concern solutions of some cases of Voigt's conjecture for integral points on affine surfaces. And I think for today I can stop here.